Inductively coupled plasma mass spectrometry is a type of mass spectrometry which is capable of detecting metals and several non-metals at concentrations as low as 1 part in 10^15 on non-interfered low background isotopes. This is achieved by ionizing the sample with inductively coupled plasma and then using a mass spectrometer to separate and quantify those ions. Compared to atomic absorption techniques, ICP-MS has greater speed, precision, and sensitivity. However, compared with other types of mass spectrometry, such as thermal ionization mass spectrometry and glow discharge mass spectrometry, ICP-MS introduces many interfering species. Argon from the plasma, component gases of air that leak through the cone orifices, and contamination from glassware in the cones. The variety of applications exceeds that of inductively coupled plasma atomic emission spectroscopy and includes isotopic speciation. Due to possible applications in nuclear technologies, ICP-MS hardware is a subject for special exporting regulations. Components. Inductively coupled plasma. An inductively coupled plasma is a plasma that is energized by inductively heating the gas with an electromagnetic coil, and contains a sufficient concentration of ions and electrons to make the gas electrically conductive. Even a partially ionized gas in which as little as 1% of the particles are ionized can have the characteristics of a plasma. The plasmas used in spectrochemical analysis are essentially electrically neutral, with each positive charge on an ion balanced by a free electron. In these plasmas, the positive ions are almost all singly charged and there are few negative ions. So there are nearly equal amounts of ions and electrons in each unit volume of plasma. An inductively coupled plasma for spectrometry is sustained in a torch that consists of 3 concentric tubes, usually made of quartz. Although the inner tube can be sapphire if hydrofluoric acid is being used. The end of this torch is placed inside an induction coil supplied with a radio frequency electric current. A flow of argon gas is introduced between the 2 outermost tubes of the torch and an electric spark is applied for a short time to introduce free electrons into the gas stream. These electrons interact with the radio frequency magnetic field of the induction coil and are accelerated first in one direction, then the other. As the field changes at high frequency, the accelerated electrons collide with argon atoms, and sometimes the collision causes an argon atom to part with one of its electrons. The released electron is in turn accelerated by the rapidly changing magnetic field. The process continues until the rate of release of new electrons in collisions is balanced by the rate of recombination of electrons with argon ions. This produces a fireball that consists mostly of argon atoms with a rather small fraction of free electrons and argon ions. The temperature of the plasma is very high, of the order of 10,000 K. The plasma also produces ultraviolet light, so for safety should not be viewed directly. The ICP can be retained in the quartz torch because the flow of gas between the 2 outermost tubes keeps the plasma away from the walls of the torch. A second flow of argon is usually introduced between the central tube and the intermediate tube to keep the plasma away from the end of the central tube. A third flow of gas is introduced into the central tube of the torch. This gas flow passes through the center of the plasma, where it forms a channel that is cooler than the surrounding plasma but still much hotter than a chemical flame. Samples to be analyzed are introduced into this central channel, usually as a mist of liquid formed by passing the liquid sample into a nebulizer. To maximize plasma temperature and stability, the sample should be introduced through the central tube with as little liquid as possible, and with consistent droplet sizes. A nebulizer can be used for liquid samples, followed by a spray chamber to remove larger droplets. Or a desolvating nebulizer can be used to evaporate most of the solvent before it reaches the torch. Solid samples can also be introduced using laser ablation. The sample enters the central channel of the ICP, evaporates, molecules break apart, and then the constituent atoms ionize. At the temperatures prevailing in the plasma, a significant proportion of the atoms of many chemical elements are ionized, each atom losing its most loosely bound electron to form a singly charged ion. The plasma temperature is selected to maximize ionization efficiency for elements with a high first ionization energy, while minimizing second ionization for elements that have a low second ionization energy. Mass spectrometry. For coupling to mass spectrometry, the ions from the plasma are extracted through a series of cones into a mass spectrometer, usually a quadrupole. The ions are separated on the basis of their mass-to-charge ratio, and a detector receives an ion signal proportional to the concentration. The concentration of a sample can be determined through calibration with certified reference materials such as single or multi-element reference standards. ICP-MS also lends itself to quantitative determinations through isotope dilution, a single-point method based on an isotopically enriched standard. Other mass analyzers coupled to ICP systems include double-focusing magnetic electrostatic sector systems with both single and multiple collector, as well as time-of-flight systems. Applications. One of the largest volume uses for ICP-MS is in the medical and forensic field, specifically toxicology. A physician may order a metal assay for a number of reasons, such as suspicion of heavy metal poisoning, metabolic concerns, and even hepatological issues. Depending on the specific parameters unique to each patient's diagnostic plan, samples collected for analysis can range from whole blood, urine, plasma, serum, to even packed red blood cells. Another primary use for this instrument lies in the environmental field. Such applications include water testing for municipalities or private individuals, all the way to soil, water and other material analysis for industrial purposes. In recent years, industrial and biological monitoring has presented another major need for metal analysis via ICP-MS. Individuals working in plants where exposure to metals is likely and unavoidable, such as a battery factory, are required by their employer to have their blood or urine analyzed for metal toxicity on a regular basis. This monitoring has become a mandatory practice implemented by OSHA, in an effort to protect workers from their work environment and ensure proper rotation of work duties. Regardless of the sample type, blood, water, etc., it is important that it be free of clots or other particulate matter, as even the smallest clot can disrupt sample flow and block or clog the sample tips within the spray chamber. Very high concentrations of salts, e.g., sodium chloride in seawater, can eventually lead to blockages as some of the ions reunite after leaving the torch and build up around the orifice of the skimmer cone. This can be avoided by diluting samples whenever high salt concentrations are suspected, though at a cost to detection limits. ICP-MS is also used widely in the geochemistry for radiometric dating, in which it is used to analyze relative abundance of different isotopes, in particular uranium and lead. ICP-MS is more suitable for this application than the previously used thermal ionization mass spectrometry, as species with high ionization energy such as osmium and tungsten can be easily ionized. For high-precision ratio work, multiple collector instruments are normally used to reduce the effect noise on the calculated ratios. In the field of flow cytometry, a new technique uses ICP-MS to replace the traditional fluorochromes. Briefly, instead of labeling antibodies with fluorochromes, each antibody is labeled with the distinct combinations of lanthanides. When the sample of interest is analyzed by ICP-MS in a specialized flow cytometer, each antibody can be identified and quantitated by virtue of a distinct ICP footprint. In theory, hundreds of different biological probes can thus be analyzed in an individual cell, at a rate of California, 1,000 cells per second. Because elements so easily distinguished in ICP-MS, the problem of compensation in multiplex flow cytometry is effectively eliminated. In the pharmaceutical industry, ICP-MS is used for detecting inorganic impurities in pharmaceuticals and their ingredients. New and reduced maximum permitted exposure levels of heavy metals form dietary supplements. Introduced in USP less than 232 greater than elemental impurities, limits in USP less than 233 greater than elemental impurities, procedures, will increase the need for ICP-MS technology, where, previously, other analytic methods have been sufficient. Metal speciation. A growing trend in the world of elemental analysis has revolved around the speciation of certain metals such as chromium and arsenic. One of the primary techniques to achieve this is to use an ICP-MS in combination with high-performance liquid chromatography or field flow fractionation. Quantification of proteins and biomolecules. There is an increasing trend of using ICP-MS as a tool in speciation analysis, which normally involves a front-end chromatograph separation and an elemental selective detector, such as AAS and ICP-MS. For example, ICP-MS may be combined with size exclusion chromatography and quantitative preparative native continuous polyacrylamide gel electrophoresis for identifying and quantifying native metal cofactor containing proteins in biofluids. Also, the phosphorylation status of proteins can be analyzed. In 2007, a new type of protein tagging reagents called metal-coded affinity tags were introduced to label proteins quantitatively with metals, especially lanthanides. The MECAT labeling allows relative and absolute quantification of all kinds of proteins or other biomolecules like peptides. MECAT comprises a site-specific biomolecule tagging group with at least a strong chelate group which binds metals. The MECAT-labeled proteins can be accurately quantified by ICP-MS down to low attomole amount of analyte, which is at least 2 to 3 orders of magnitude more sensitive than other mass spectrometry-based quantification methods. By introducing several MECAT labels to a biomolecule and further optimization of ICP-MS detection, limits in the zeptomole range are within the realm of possibility. By using different lanthanides, MECAT multiplexing can be used for pharmacokinetics of proteins and peptides or the analysis of the differential expression of proteins, e.g., in biological fluids. Breakable page SDS page, two-dimensional gel electrophoresis or chromatography is used for separation of MECAT-labeled proteins. Flow injection ICP-MS analysis of protein bands or spots from DPAGE SDS page gels can be easily performed by dissolving the DPAGE gel after electrophoresis and staining of the gel. MECAT-labeled proteins are identified and relatively quantified on peptide level by MALDI-MS or ESI-MS. Elemental analysis. The ICP-MS allows determination of elements with atomic mass ranges 7 to 250, and sometimes higher. Some masses are prohibited, such as 40, due to the abundance of argon in the sample. Other blocked regions may include mass 80 and mass 56. The latter of which greatly hinders Phe analysis unless the instrumentation is fitted with a reaction chamber. Such interferences can be reduced by using a high-resolution ICP-MS which uses 2 or more slits, constricts the beam and distinguish between nearby peaks. This comes at the cost of transmission. For example, to distinguish iron from argon by take a resolving power of 10,000, which may reduce the ion transmission by around 99%. A single collector ICP-MS may use a multiplier in pulse counting mode to amplify very low signals, an attenuation grid or a multiplier in analog mode to detect medium signals, and a Faraday cup bucket to detect larger signals. A multi-collector ICP-MS may have more than one of any of these, normally Faraday buckets, which are much less expensive. With this combination, a dynamic range of 12 orders of magnitude, from 1 ppq to 100 ppm is possible. ICP-MS is a method of choice for the determination of cadmium in biological samples. Unlike atomic absorption spectroscopy, which can only measure a single element at a time, ICP-MS has the capability to scan for all elements simultaneously. This allows rapid sample processing. A simultaneous ICP-MS that can record the entire analytical spectrum from lithium to uranium in every analysis won the Silver Award at the 2010 Pitkin Editors Awards. An ICP-MS may use multiple scan modes, each one striking a different balance between speed and precision. Using the magnet alone to scan is slow, due to hysteresis, but is precise. Electrostatic plates can be used in addition to the magnet to increase the speed, and this, combined with multiple collectors, can allow a scan of every element from lithium-6 to uranium oxide 256 in less than a quarter of a second. For low detection limits, interfering species and high precision, the counting time can increase substantially. The rapid scanning, large dynamic range and large mass range is ideally suited to measuring multiple unknown concentrations and isotope ratios in samples that have had minimal preparation. For example, seawater, urine, and digested whole rock samples. It also lends well to laser-ablated rock samples, where the scanning rate is so quick that a real-time plot of any number of isotopes is possible. This also allows easy spatial mapping of mineral grains.